In this video, I will be discussing about mixture problems. Now, to illustrate this physical application of differential equation, allow me to illustrate using a drawing. I have here a tank that contains some volume of solution inside. And we have here an inlet pipe that flows another solution towards the content of this tank. So this one is an inflow of another solution. And you can see also that there is another pipe which is an outlet pipe that flows the content outside the tank. So this is the outflow of the content of the tank. Now remember that at the start, the tank contains a solution in it. And let us represent this one as V. And suppose the content is a salt solution, we can represent our X as the amount of salt in the solution. Now this amount of salt in the solution is affected by the rate of inflow of another solution from the inlet pipe, and also is secondly affected by an outflow of the mixed solution inside the tank. So let us represent this amount of salt inside the tank at any time t. Now there are two things that we should consider here. First, the volume is changing inside the tank. Now take note that the volume of the content inside the tank is constant when the rate of inflow of another solution is equal to the rate of outflow of the mixture of solution escaping from the tank. So here, let us consider first the change of the volume of the solution inside the tank. And this can be represented using calculus as dV dt. In other words, the change in the volume at any time t, which can be calculated using the rate of solution flowing inside the tank minus the rate of solution escaping from the tank. Now take note that there is only a change of the volume if the rate of the inflow is not equal to the rate of outflow. Because if the rate of inflow is equal to the rate of outflow, there will be a constant volume of solution inside the tank. And then second is the change of the amount of solute inside the tank. And this can be represented using calculus as dx dt. So the change of the amount of solute with respect to time. And this can be calculated by the amount of solute flowing inside the tank. So this is dx dt, a change of the amount of solute flowing towards the tank minus the change of the solute moving out or escaping from the tank. So we will write here that dx dt is the rate of change of the amount of solute in the tank. So this is the meaning of this dx dt. And the dx dt in is the rate of amount of solute moving towards the tank, entering the mixture inside the tank. And dx dt out is the rate of amount of solute escaping from the tank. And this rate of the change of the amount of solute entering the mixture inside the tank can be computed by the product of the rate of solute entry per unit volume. And this is multiplied by the rate of entry in liters. And also this rate of change of the amount of solute escaping from the mixture inside the tank can be computed by the product also of the rate of the resulting solute per unit volume. which will be multiplied by the rate of escape in liters. So therefore, mathematically, our dx dt can be computed by the rate of solute entry per unit volume, which can be represented as CI, rate of solute of entry, I means inside the tank, times the rate of entry going inside the tank. And this will be subtracted by this rate of the resulting solute per unit volume. And this rate of the resulting solute per unit volume is represented by CO, because this is the rate of the resulting solute per unit volume escaping from the tank. O means outside, and this will be multiplied by the rate of escape, which will be represented by R sub O. So this is now our formula that will be used in solving mixture problems that can be modeled by differential equations. So let's have our first example here. A tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Brine that contains 0.03 kilogram of salt per liter of water enters the tank at the rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt remains in the tank after half an hour? So first, let us draw the inlet pipe towards the tank. So this is the inlet pipe whose job is filling the tank by some solution. There is also another outlet pipe of this tank. So this is the inlet pipe, this is the outlet pipe. Now remember that this tank also contains some solution inside. Now in this solution, the volume is 5,000 liters of water, of which we dissolve 20 kilograms of salt. So the solution inside the tank is 5,000 liters of water, of which we dissolve 20 kilograms of salt. Now take note that the inflow rate here is 25 liters per minute, which is of the same rate of the outflow, because it is given in the problem that they have the same rate. However, we must take note that the amount of salt flowing inside the tank is having a content of 0.03 kilogram per liter. So our objective here in this problem is to find how much salt remains inside the tank after half an hour. So that's the one that we are going to represent here. Let X be the amount of salt, and the rate of change of the amount of salt can be represented by dx dt, which can be calculated by the rate of salt entry using the inlet pipe minus the rate of the amount of salt escaping from the tank using the outlet pipe. So this is dx dt, which is equal to the rate of solute entry per unit volume times the rate of entry in liters minus the rate of the resulting solute per unit volume moving outside the tank times the rate of the outflow using the outlet pipe. So using the given numbers in the problem, we have our C sub I as 0.03 kilograms per liter, because this is the amount of salt per liter moving inside the tank, and the rate of inflow is 25 liters per minute. And take note that to find the salt in the mixture inside the tank at any time t can be represented by x of t per unit volume. But we know that the volume is constant. Why? Because the rate of inflow is the same as the rate of outflow. So all the time, the volume of the mixture inside the tank is constant. It will not increase nor decrease, because although there is an inflow of another solution inside the tank, there is also the same rate of outflow of the mixture outside the tank. So therefore, the representation of the rate of the resulting solute per unit volume is changing at any time t over the volume of 5,000. So this is, of course, in kilogram per liter. And this will be multiplied also by our rate of escape using the outlet pipe, which is the same as the rate of inflow using the inlet pipe. So we have here the x dt is equal to the product of this one. And the product of this is equal to 0.75 kilogram per minute, because the liters there will be cancelled there. And if you multiply this one with this, we have x of t over 200. And the unit here is also kilogram per minute, because again, the liters will be cancelled here. So factoring our units of measurement, we have here 0.75, which is 3/4 in fraction, minus x over 200 kilograms per minute. So we did not write anymore t, because this solute inside the tank is changing over time. Then therefore, the resulting equation is a differential equation which can be solved using the techniques we've learned from our previous videos. Now we notice that this differential equation can be solved by using the technique of separating the variables. So by separation of variables, we can write dx over 150 minus x, which is equal to dt over 200. And this can be done by exchanging these quantities here. And that is simply an algebra. Now, taking the integral of both sides of this equation, we notice that if this is our u, our du must be negative dx, because the derivative of 150 is 0, but the derivative of negative x is negative 1. So negative 1 dx, we need a negative outside the integral symbol so that we can write also negative dx inside the integral symbol, so that when you multiply, that cancels each other. So this is also equal to 1 over 200, because this is a constant, times the integral of dt. And you simply notice that if this is our u, our du is in the numerator. So the integral of this is the natural log of our u, which is 150 minus x. So this is equal to t, which is the integral of dt over 200. And of course, there is a constant of integration here, c. Now let us represent this equation as our equation 1. Now, our next goal is to find the value of our constant of integration. So we use here some boundary conditions in the problem. And we know that at time 0, we have the amount of salt inside the tank, which is equal to 20 kilograms. Then we can write this one as the negative of the natural log of 150 minus 20, because our value of x is 20 this time, which is equal to 0 over 200, because this is at the start, so our t is 0 plus the constant of integration c. So, solving simple arithmetic, we have the negative of the natural log of 130, which is equal to our constant of integration c. Hence, our c is the negative of the natural log of 130. Thus, our equation is the natural log of 150 minus x, which is equal to t over 200 minus the natural log of 130. But our goal here is to find our x, the amount of salt inside the tank after 30 minutes. So we need to solve for our x here. But this can be done by isolating all the natural logs to one side of the equation. So we have negative t over 200, which is equal to the natural log of 150 minus x. So this is positive at the right minus the natural log of 130. And using the property of logarithms, we can rewrite this as negative t over 200, which is equal to the natural log of 150 minus x over 130. Then, transforming this logarithmic equation to its equivalent exponential form, we use this one as the exponent to the natural base of e. So e to the power of negative t over 200 is equal to 150 minus x over 130. And you can multiply both sides of the equation by 130. So this is 130 times e to the power negative t over 200 is equal to 150 minus x. So therefore, our x is equal to 150 minus 130 times e to the power of negative t over 200. So therefore, we can find our amount of salt after half an hour. So the amount of salt after 30 minutes, because we need to convert half an hour to minutes to be unified with our units of inflow, which is 25 liters per minute. We have x, which is equal to 150 minus 130 e to the power negative 30 over 200. But this exponent fraction can be simplified as negative 3 over 20. And using our calculator, we know that e to the power negative 3 over 20 when multiplied to negative 130 is equal to negative 111.89. So the amount of salt inside the tank is equal to 38.11 kilograms of salt after 30 minutes, which is half an hour. So the salt inside the tank here is increasing from 20 kilograms. After 30 minutes, it became 38.11 kilograms. Now, let's proceed to our second example here. A 150-gallon tank initially contains 90 pounds of salt dissolved in 90 gallons of water. Brine containing 2 pounds per gallon of salt flows into the tank at the rate of 4 gallons per minute, and the well-stirred mixture flows out of the tank at the rate of 3 gallons per minute. How much salt does the tank contain when it is full? This problem is different from the first problem that we had because the rate of inflow is not the same as the rate of outflow here. So the volume of solution inside the tank is changing here because the rate of inflow is 4 gallons per minute, but the rate of outflow is 3 gallons per minute. So you see, for every minute, there is an additional of 1 gallon here. 1 gallon inside the tank, because every minute there will be an additional 4 gallons of solution, and at the same time there will be a loss of 3 gallons per minute there. So 4 minus 3, the result is 1. So every minute there is a gain of 1 gallon of solution inside the tank. Unlike with our first problem, that the volume is constant, because the rate of inflow is the same as the rate of outflow there. So you should not be confused that the very interesting feature of this example is that due to the differing rates of inflow and outflow, the volume inside the tank is not constant. So let's represent the amount of salt inside the tank. So let X be the amount of salt, which can be represented using calculus as dx dt, which is equal to the rate of change of the salt, because there is an inlet pipe flowing inside the tank, but there is also a solution that will be flowing outside the tank because of the outlet pipe there. So solving for our dx dt, we have 2 pounds per gallon, because that's the amount of salt flowing into the tank, but the rate of inflow is 4 gallons per minute. But this will be subtracted also by the rate of salt outflow. So this is represented by X over 90 plus 1T here. Now, maybe you ask a question, where did I get 90 plus 1T? Remember that the volume inside the tank at the start is 90 gallons of water. But every minute there is a gain of 1 gallon, because the rate of inflow using the inlet pipe is 4 gallons per minute. And we have the rate of outflow of 3 gallons per minute. So there is a gain of 1 gallon every minute. So we have here 1T. And this 1 is coming from rate of inflow minus the rate of outflow. So 4 minus 3 is equal to 1. But the unit of measurement here is pounds per gallon. And this will be multiplied by the rate of outflow, which is 3 gallons per minute. So we have dx dt, which is equal to 2 times 4, which is 8 pounds per minute here, because the gallons will be cancelled there. But this will be subtracted by 3x over 90 plus t, and the unit of measurement is pounds per minute. So we have our dx dt here as 8 minus 3x over 90 plus t. So we factor out the unit of measurement, which is pound per minute outside. And we notice that if we move this negative fraction to the left, we have dx dt plus 3 over 90 plus tx, which is equal to 8, as the first ordered linear differential equation. So this is a first ordered linear in x. So since this is a foldy where this fraction is our a of t here, and this expression at the right hand side of the equation as our b of t. So we've learned already how to solve a first ordered linear differential equation by finding our integrating factor phi of t, and phi of t is equal to e to the power of the integral of a of t dt. And we know that our a of t is equal to 3 over 90 plus t dt here. So integrating this one, we can simply factor out this constant outside the integral symbol. We have e to the power of 3 times the integral of dt over 90 plus t here. And we noticed that this is easily integrated because if this is our u, our du is in the numerator. So this is the integral of du over u. So the integral is the natural log of our u, which is 90 plus t. So our integrating factor is equal to e to the power of the natural log of 90 plus t to the power of 3. By applying the properties of logarithm, that this 3 can be the exponent of 90 plus t. And applying further another property of logarithm, we have e to the power of the natural log that cancels each other. So what remains is 90 plus t to the power of 3. So this is now our integrating factor. So then we can solve this first ordered linear differential equation by writing our x times the integrating factor phi of t, which is equal to the integral of the phi of t times the b of t dt. And we know that our integrating factor is 90 plus t to the power of 3, which is equal to this integral of phi of t, which is again 90 plus t to the power of 3. But our b of t is 8, so 8 can be factored outside the integral symbol. So 8 times the integral of 90 plus t to the power of 3 dt here. So this is equal to x times 90 plus t to the power of 3. So using the power rule in integration, we have 8 times 90 plus t to the power of 4, because we add 1 when we integrate this exponential form. And we divide also by 4 plus the constant of integration c. So therefore, our resulting equation will be x plus 90 plus t to the power of 3, which is equal to 2 times 90 plus t to the power of 4 plus the constant of integration c. But we can solve for this constant of integration c if we use a boundary condition from the problem, that we know that at time 0, meaning at the start, the amount of salt solution is 90 inside the tank, 90 pounds. So we have 90, so we substitute our x here, times 90 plus 0 to the power of 3, which is equal to 2 times 90 plus 0 to the power of 4 plus the constant of integration c. So simplifying further, we have 90 to the power of 4, because 90 plus 0 is 90, and 90 to the power of 3 times 90, the result is 90 to the power of 4. So this is also equal to 2 times 90 to the power of 4 plus the constant of integration c. However, if we move this one to the left side of the equation, we have 90 to the power of 4 minus twice of 90 to the power of 4, which is equal to the constant of integration c. So 1 minus 2 is negative 1. So this is negative of the fourth power of 90 here. So this is our constant of integration. Thus, our equation, which is this one, becomes x times 90 plus t to the power of 3, which is equal to 2 times 90 plus t to the power of 4 minus the fourth power of 90. But solving for x by dividing both sides of the equation by the cube of this 90 plus t, we have x, which is equal to 2 times 90 plus t minus the fourth power of 90 divided by 90 plus t to the power of 3. Now take note that the full capacity of the tank is only 150 gallons, and we know that the initial amount of water inside the tank was 90. So there is an empty space of 60 gallons there. But 60 gallons can be achieved in just 60 minutes because there is a gain of 1 gallon per minute due to the inflow rate of 4 gallons per minute minus the outflow rate, which is 3 gallons per minute. In other words, there is a gain of 1 gallon every minute inside the tank. So we write here, but the tank will be full in 60 minutes here. So when t is 60, we have 2 times 90 plus 60 minus the fourth power of 90 divided by 90 plus 60 to the power of 3. We have our x as 300 because 90 plus 60 is 150 and 150 times 2 is 300. And using our calculator, this fraction is equal to 19.44. Hence, the amount of salt inside the tank when it is full is equal to 280.56 pounds of salt. So this is the amount of salt present in the tank when it is full. Now let's proceed to our example number 3. Assume that the Lake Baho has a volume of 480 kilometers cubed and its rate of inflow from Lake Bati and outflow to the Lake Awas are both 350 kilometers cubed per year. Suppose that at time t, which is equal to 0, meaning at the start, the pollutant concentration of Lake Baho, which is caused by past industrial pollution that has now been ordered to cease, is 5 times that of Lake Bati. If the outflow from Lake Baho henceforth is perfectly mixed lake water, how long will it take to reduce the pollution concentration in Lake Baho to twice that of Lake Bati? So here, let us draw first our Lake Baho. So if this is our Lake Baho here, so the water is flowing here because this is our Lake Baho, and the volume here is 480 kilometers cubed. This Lake Baho receives also a flow of water from Lake Bati. So of course this is another lake that is flowing inside Lake Baho, which we call here Lake Bati. So there is an inflow of water from Lake Bati to Lake Baho here, and the rate of inflow is 350 kilometers cubed per year. And of course, this Lake Baho also has an outflow towards another lake. So here, there is another lake here. We call this one as the Lake Awas. But the outflow rate of this Lake Baho to Lake Awas is the same as the inflow from Lake Bati, which is 350 kilometers cubed per year. So there is an inflow of water towards Lake Baho from Lake Bati, and there is also an outflow of Lake Baho towards Lake Awas here. Now, suppose that at the time zero, meaning when the environmentalist or the scientist noticed that Lake Baho is already polluted, they recommended to the government to stop the industrial pollution which causes this lake to be polluted, because they noticed that the pollution in Lake Baho is 5 times as the pollution in Lake Bati. Now the question is, if the outflow from Lake Baho henceforth is perfectly mixed lake water, so the existing lake water which is 5 times as polluted as Lake Bati, then how long will it take to reduce the pollution of this Lake Baho to be twice as much as the pollution in Lake Bati? Because the pollution caused by industrial factories is already stopped at this time. So let's represent our variables here. Let X be the amount of pollutants and C as the amount of pollutant of the Lake Bati, because the amount of pollutants in Lake Bati was not given in the problem. Only a relationship that the pollution in Lake Baho is 5 times as the pollution in Lake Bati. So to represent the amount of pollutants in Lake Baho, which is 5 times, we represent that one as 5C, so that this will be 5 times as much of Lake Bati. So this is the amount of pollutants in Lake Baho. So here, let us represent the change in the amount of pollutants in Lake Baho as the rate of pollutants coming in from Lake Bati minus the amount of pollutants moving outside Lake Baho towards Lake Awas. So this is dx dt, which is equal to the amount of pollutants coming in times the rate of flowing inside Lake Baho from Lake Bati minus the resulting pollutants inside Lake Baho moving outside to Lake Awas times the rate of outflow of Lake Baho. And this can be represented as C, the amount of pollutants coming in from Lake Bati, times the rate of inflow, which is 350 kilometers cubed per year. But I will not write 350 there. And I just remember that that's constant inflow, which is the same as the rate of outflow towards Lake Awas, minus the amount of the resulting pollutants in Lake Baho, which is a mixture of the pollutants from Lake Bati and the existing pollutants from Lake Baho. So this is represented by X over the volume of the water in Lake Baho, which is constant because the rate of inflow is the same as the rate of outflow, times the rate of outflow, which is 350, the same as the rate of inflow from Lake Bati. And rewriting this equation, we have dx dt minus the negative of r over v times x, which is equal to CR here. Since this is negative at the right, it becomes positive at the left. And we notice that this is a first-ordered linear differential equation, linear in x. So we identify that this one is our a of t, and the right-hand side of the equation is our b of t. So solving this first-ordered linear differential equation in x, we need to solve for our integrating factor phi of t. And phi of t is equal to e raised to the integral of a of t dt. And we know that our e of t is r over v dt. So our variable of integration here is t. So we treat r and v as constants here. So e to the power r over v, if we factor that one outside, we have e to the power r over v t. So this is our integrating factor here. Then we can write our solution as x times the integrating factor phi of t, which is equal to the integral of the integrating factor phi of t times b of t dt. And substituting our integrating factor, which is this one, we have x times e to the power r over v t is equal to the integral of e to the power r over v t times the b of t, which is cr from here times dt. So solving this one, we have x times e to the power r over vt, which is equal to cr, because cr is considered constant here since the variable of integration is t, times the integral of e to the power r over v t times r over v dt. Because if this is our u, the du must be here. And maybe you ask, where did I get this r over v? So I get this r over v from somewhere, because I just multiply also here v over r, so that v over r times r over v, the product is 1, as if I have done nothing to the equation. So we have x times e to the power r over v t, which is equal to vc times e to the power r over v t plus the constant of integration c. Now we can solve for this c if we use a boundary condition from the problem. And the boundary condition that we know is that at the time 0, meaning at the start, the amount of pollutants in Lake Baho is 5 times the amount of pollutants of Lake Bati here. And we can substitute this x here to our equation. So we have 5bc times e to the power r over v times 0, because our time is 0, is equal to vc times e to the power r over v times 0 plus the constant of integration c. So we have 5bc times 1, because the exponent here is 0, so e to the power 0 is 1, which is equal to vc times also 1, because the exponent also here is 0 plus the constant of integration c. So 5bc minus 1vc is equal to the constant of integration c. Hence, our c, which is the constant of integration, is 4vc. Thus, our equation becomes x times e to the power r over v t, which is equal to vc times e to the power r over v t plus 4vc. And solving for x, we can divide both sides of the equation by this e to the power r over v t. So we have x, which is equal to vc plus 4vc over e to the power r over v t. Or you may write this one as x, which is equal to vc plus 4vc times e to the power negative r over v t. Hence, to find the time when the amount of pollutants in Lake Baho will be twice as the amount of pollutants in Lake Bati. So we write here that to find t when the amount of pollutants in Lake Baho will be x, which is equal to twice of the pollutants in Lake Bati. So substituting this one to this equation here, we have 2VC, which is equal to VC plus 4VC times e to the power of negative r over Vt. So 2VC minus VC is just VC here. And this is equal to 4VC times e to the power negative r over Vt. But we can divide both sides of the equation by VC. So 1 is equal to 4 times e to the power negative r over Vt. So dividing both sides of the equation by 4, we have 1/4 is equal to e to the power negative r over Vt. Hence, applying the properties of logarithm, we have t, which is equal to v over r times the natural log of 4. And since the volume is 480 kilometers cubed and the rate of outflow and the inflow, which is 350 kilometers cubed per year, we substitute this v and r to this equation here and then solve that our t is equal to 1.9 years. So therefore, it will take almost 2 years for the amount of pollutants in Lake Baho to be as twice as the amount of pollutants in Lake Bati. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.